Hello everyone, my name is Michael Caduro and I would like to introduce you to my team, Gabriela Defina, Nicola Renzen, and Jenna Rotondi. We're all passionate fourth-year co-op students with practical engineering experience and share a strong interest in sports and rehabilitation. Today, we are going to share our design for an ergonomic wrist cast for youth that is breathable, waterproof, lightweight, and inexpensive. In this section, we will be discussing the problems with current casting methods, frequency of fractures in youth, the project scope, and the constraints and criteria for the design. The main objective of casts is to immobilize an injured body part to prevent further injury and allow for the healing process to begin. Currently, most wrist fractures are treated using either a fiberglass cast or a plaster of Paris cast. However, these traditional casting methods come with several issues. Plaster and fiberglass casts have been known to be hard to clean, making it difficult to be able to maintain proper hygiene, causing sores and rashes. Cast complications such as treating infections, replacing water damaged casts, and remolding improperly fitted casts result in hospitals spending valuable time and resources retreating patients. Additionally, harmful dust is produced when removing plaster casts, irritating mucous membranes in the nose, throat, and lungs. Finally, plaster casts are very bulky and uncomfortable, taking up unnecessary space around the arm when immobilizing the wrist. Although fiberglass casts are slightly smaller in size, there is lots of room for improvement within this area, as well as several others.
The targeted demographic for this project is aimed towards youth ages 5 to 17. This is due to 25% of all fractures for this age group being distal radial fractures. It's common for the treatment for these fractures to be about 6 weeks in length. Due to the duration of cast wear and the nature of children, the team focused on the casts that would comply with the typical lifestyle of a user within this age range. This includes accounting for swimming, bathing, and sweating from various activities. To comply with standard safety regulations, the following standards were used when designing this product. ISO 13485 outlines the quality management system and associated regulations for a medical device. ISO 10993-10 is to ensure the material used is biocompatible, and ASTM F1555-94 is the guideline for extremity splints and that they must properly immobilize the injury. These standards were used as guidelines for designing this product to adhere to safety regulations. Additionally, this product is denoted to be a Class 1 medical device as per the Health Canada guidelines. The problem statement. The team will aim to design a wrist cast to be used by youth to improve upon current plaster of Paris and fiberglass casts. The cast will be breathable, waterproof, lightweight, and inexpensive.
The scope of this project includes choosing the correct material and functional limits for a short arm cast for distal radius fractures in youth. Many design alternatives have been proposed, and a full 3D model has been completed for the chosen alternative. These designs will be addressed more specifically later on in our presentation. Supporting simulations such as finite element analyses and other calculations such as total mass, costs, and manufacturing time have been conducted and will continue to be refined. The design will be completed for only one wrist size, and no physical prototype will be developed at this time. The integration or creation of 3D scanning software will not be addressed, nor will the recycling process of the product. There are many constraints that will help define the designs created. The cast must be customizable so it can be used for children of all ages. It must be waterproof so the user can bathe and or swim with the cast on. And to ensure the safety of the cast, it must be able to withstand a 100 Newton one-time force and 10 Newton repetitive forces for 500 cycles. The cast must be able to be cleaned easily, and to abide by the previously mentioned ASTM standard, the product must be able to be cleaned without the retention of cleaning agents. Many criteria were used to determine the best design alternative. These include minimizing the waste for the life cycle of the product, maximizing the comfort of the cast, minimizing its weight, as well as ensuring it is slim-fitting and aesthetically pleasing. The time in which the patient remains without a cast after being diagnosed with a fracture should be minimized, and this will allow for the healing of the fracture to begin in the correct position as soon as possible. The factor of safety for the cast should be maximized. This factor of safety will be determined by the ratio of the yield stress of the chosen material to the maximum stress present in the cast.
The design approach used to solve the presented problem for this project will be discussed next. The process of this project included many steps between the initial problem statement creation to the completion of the detailed final design. First, the team conducted research to gain a better understanding of the problem, finding the specific areas requiring improvements, and a problem statement was created. The conceptual design steps included information gathering, concept generation, and the evaluation of these concepts. Alternative designs were proposed, and we selected a final design through the use of multiple design tools. The embodiment design steps were completed after the proposed preliminary design was determined. Material selection, modeling, and final design decisions were conducted until a detailed design was finalized by the team that met the requirements of the problem statement. Within the concept generation step of the design process, 4 alternative designs were presented and thoroughly researched to be able to solve the presented problem. The first proposed design was an air cast that was based off of the walking boot design that is currently used for ankle and foot injuries. The next alternative design was a fully 3D printed cast with a mesh structure and snap hooks. The next alternative design incorporated multiple materials that included a 3D printed structure and an inserted material to increase comfort on the user's skin. The final design alternative was an adjustable, reformable cast that would use a thermoplastic for initial shape creation and dial for adjusting the tightness. The next step in the design process was to evaluate the generated concepts using a decision matrix. The decision matrix weighed the alternative strengths and weaknesses for each of the defined criteria. The result of this decision matrix was confirmed by completing 2 sensitivity analyses, one focusing on the best interests of the user and one focusing on the best interests of the stakeholders. The results determined that the fully 3D printed cast would be the most suitable design to solve the presented problem. Design tools and software that were used in the design process included SOLIDWORKS to create 3D models of the final design, ANSYS to conduct finite element analyses to confirm the safety of the design, and Ultimaker software to estimate print times of the final design. The results of using these tools will be discussed in the next section.
We will now be discussing the specific components of our chosen design, highlighting its design features, functionality, safety, and many impacts socially, environmentally, and economically. Our design solution takes advantage of the creative freedoms associated with 3D printing technology. By using a 3D scanning device to determine the contours of the patient's hand, arm, and wrist, we can develop custom cast geometries for each user, producing a sleek and compact design while increasing comfort. Pairing this technology with 3D printing allows for little to no waste during the manufacturing process. This also allows the manufacturing process to be completed entirely within the hospital and does not require any external outsourcing. Finally, one of the largest benefits of this design is that it is not susceptible to water damage, giving patients the ability to swim and bathe with ease and peace of mind. The cast is extremely light and will have minimal impact on daily life. Polypropylene was selected as the material for the design because it has an exceptional strength-to-weight ratio, a moderate cost, and is environmentally friendly due to its ability to be thermomechanically recycled. This makes polypropylene a great choice for an immobilization device with such a small operational period. To be able to minimize the amount of material used in the design while maintaining the mandatory strength, a hexagonal mesh pattern was chosen to be used on the body of the cast. This pattern has been proven to be strong and is aesthetically pleasing, which makes it an ideal choice for this design. Finally, the design features 2 halves that are connected by means of snap hooks and grooves along the exterior of the cast. The snap hooks will allow for a minimalistic approach to fastening both pieces and will prevent accidental disassembly by the user when they are enjoying their typical everyday activities.
We will now discuss the defense of our design by addressing the functionality, safety, costs, and potential risks. The functionality of this product is based on its ability to properly immobilize the wrist for the duration of the treatment process. This entails maintaining the same structural integrity throughout its use. The design also includes a slim and comfortable fit to allow little to no movement of the wrist. It also achieves the constraints outlined. This includes breathability, waterproof, protective, lightweight, and comfortable. The printing time is also expected to range between 3 and 6 hours. Each half will be printed individually to maximize time and is subject to change based on the printer grade and cast size. To ensure the safety of this device, a finite element analysis was performed using ANSYS, and a 100-Newton force was applied in critical areas of the cast that were determined from typical daily activities with the arms. Additionally, hand calculations were done to determine the stress concentration factors due to the hexagonal pattern. As outlined in the constraints, the factor of safety target was 2. Both analyses confirmed the factor of safety objective was exceeded, thereby ensuring the product is safe for use and cannot be broken when a sudden weight is applied. Additionally, polypropylene is a safe material that is unlikely to cause irritation throughout the cast's use. Finally, a fatigue test will be conducted to ensure the product will withstand the duration of treatment.
There are many social impacts of this product that benefit both the patient and the healthcare system. This cast allows for much better hygiene practices, which in turn prevents return trips to the hospital to treat issues such as sores. This cast is waterproof, which not only allows the user to bathe with the cast on, but also allows them to participate in activities that they enjoy, such as swimming. The cast being waterproof also limits the incidence of return visits to the hospital for the purpose of recasting the injury if there was water damage to the cast. The mesh design of the cast makes it more breathable, and all of these factors together provide the user with a more enjoyable casting experience. This cast has very minimal effects on the environment. The polypropylene material can be melted down and reused to manufacture new casts. This is unlike current plaster of Paris and fiberglass casts, which just end up in the landfill. The manufacturing of the cast can also be done all electrically, so when the right infrastructure is in place, it can be manufactured using clean energy. The overhead costs needed to fully implement this cast manufacturing process in a hospital are quite high. This is partly because commercial 3D printers are recommended because of their increased print volume and speed. A 3D scanner as well as CAD software will also be needed. Additionally, one or more staff will need to be trained to use the equipment and the CAD software. However, the cost of the material needed to make this cast is cheaper than the cost of both the plaster of Paris and fiberglass casts. To see how many 3D printed casts would need to be manufactured for the savings in material cost to amount to the overhead costs, a fairly conservative approach was used. This includes using the cost of a larger 3D printed cast and the cost of the less expensive plaster of Paris cast. The number of casts where the savings begin to outweigh the overhead costs is 5,268. For a hospital serving a region of approximately 100,000 youth, 3,610 individuals would be diagnosed with a fracture per year. This patient flow results in a payback period of just under a year and a half. Potential risks that may be encountered in the continuation of this project include the possible risk of the cast breaking if it is exposed to forces beyond the intended limits. Also, individuals may possibly have an allergic reaction or other skin irritation because of the material on their skin. However, this risk is low because polypropylene has been proved to be generally safe for skin contact. Lastly, the generation of aerosols may be a risk when the product is being 3D printed, but this risk can be mitigated if the room is well ventilated or the commercial-grade printer is enclosed and has a filter installed. These risks will be addressed in depth before the system is implemented into a hospital. Uncertainties affiliated with this project include the validation of the solutions due to the assumptions made for the calculations and the simulations. The availability of 3D printers and scanners, as well as potential technical issues with this equipment, is uncertain and may affect each location differently. The true comfort of the cast cannot be determined until a final prototype is created, which is not included in the scope of this project. Lastly, the availability of funding to implement this full process is subject to change.
The next steps for this project would include the creation of a prototype to conduct real-world safety and comfort testing. Determining the process for 3D scanning and printing will be required to create a seamless transition between the two necessary design steps that are needed per cast creation. We plan to work on an application to become a certified Class 1 medical device in Canada. Lastly, we plan to reach out to hospitals or current clinics to implement user feedback and to discuss funding options. Overall, the next steps of this project will allow us to start the implementation of the final design, determine initial results, and adapt as needed to improve the issues presented for youth who experience wrist fractures. On behalf of my team, I'd like to thank you for listening, and we hope you enjoyed our presentation.